All right, hello. We're going to go over some gas stoichiometry problems, which just means stoichiometry applied to gases, as the name says, and is nothing different than just normal reactions with using the ideal gas law. That's pretty much all it is. In this first example, we have a problem where we have a gas collected over water. So when you see this term collected over water, there is an important part of the problem that to kind of diagram out would mean you would have, let's say, some kind of reaction happening that's producing gas, right? So here's your reaction, some flask, and then you have a container that initially has water in here, let's say. So from your reaction, the gas that's produced goes into the container with water, and that pushes out the water into another container. And so the amount of water that has been displaced is equal to the volume of gas that's produced, right? This is just displacement of water. And in these kind of problems, the thing to keep in mind is that when you're measuring this total pressure, so this kind of pressure up here above the water is a sum of the pressure of the gas you're collecting, which in this case is nitrogen, plus the amount of water vapor. So whenever you have liquid water, above that water, you'll also have some water vapor, some particles of water in the gas phase. And that's the key, that you need to keep that in mind. And that's why this is given, and usually will be given in the problem as a hint that you'll probably need that in some kind of calculation. So in this case, I'm just going to change the gas to nitrogen. And we'll first figure out the pressure of nitrogen by subtracting the water vapor from the total pressure. And the total pressure sometimes is also just known as the atmospheric pressure. In this case, it's given in torr. And we'll subtract the pressure of water, which is also in torr. So this is 702.2 torr, okay, which we can convert to atmospheres by dividing by 760, 0.924 atmospheres, okay. So that's the main idea. The rest is just plugging it into the ideal gas law. Scroll down. So now we're just going to use that to find the moles. And if we divide both sides by RT, we have a pressure of the nitrogen. We have the volume, which is given in milliliters. So that's 0.0318 liters. And then R, which is our gas constant. And the temperature, which is given in Celsius, and that's 25 degrees, which is 298 Kelvin. So again, this is just information that I'm pulling from here. So that again is referring to how much nitrogen gas was collected here and that temperature. And that's equal to 0.0012 moles of nitrogen gas, N2. And then we can use the molar mass, 28 grams per mole. That's 0.0336 grams of this nitrogen gas that was collected. Okay, so pretty straightforward. Just remember the collected over water part. You need to subtract the water vapor, and that's pretty much it. With this one, we have a reaction. We're going to have to write the reaction first. We have oxygen gas reacting with solid carbon to form carbon monoxide. And we want to balance this. So we'll need a 2 in front of the carbon, a 2 in front of the carbon monoxide. Okay, so we have 2.5 moles of oxygen reacting with 3 moles of the solid carbon. We want to know what will be the final pressure after the reaction. This is going to react completely. So this is a limiting reaction problem. That's where the stoichiometry comes into play. There's a couple ways to do this. So I'll first go through just the normal way we do it with stoichiometry using moles, and I'll show you a way that can be used in, quote unquote, gas stoichiometry problems, where we can use different units that are proportional in terms of stoichiometric ratios and all that. Okay, so we're going to find the limiting reactant. And I'll do it the normal way, where we take the moles of oxygen, convert it to moles of product. This is going to be 5 moles of CO produced. 3 moles of carbon will make, this is basically a 1-to-1 ratio, so we get 3 moles of CO. Okay, so we can't make 5 moles because we're going to run out of carbon. The limiting reactant is the carbon, and we know that we're going to have 3 moles of product produced. Okay, so some times, you might just, or some people might just plug that into the ideal gas law, find the pressure, and then be done. But that would be missing an important thing, which is that in this container, there is still leftover oxygen. So because that's a gas, that's going to contribute to the total pressure. So before we use the ideal gas law, we have to remember that we want to find the excess oxygen. So to do that, we're going to do what we normally do, where we take our initial moles of oxygen and subtract the amount used to get the excess. So the amount used, if we know the limiting reactant is carbon, we're going to use 1 mole of O2 for every 2 moles of carbon used. So we're going to use 1.5 moles of oxygen. And that's going to go here. So then we get 1 mole O2 excess left over. Okay, so we have the 3 moles of CO that are produced, the 1 mole of oxygen excess, and now one way to do this problem is to find the pressure of carbon monoxide and the pressure of oxygen and add those pressures together, which works. Or we can just do the ideal gas law once, and by finding the total moles, we can find the total pressure. So when we do this ideal gas law, instead of doing it individually, we're going to do the total, which would be 3 moles of CO plus 1 mole of oxygen. That adds up to 4 moles total. And then we have R, of course. Just leave out the units. So this is 296, 23, yeah, 23 degrees, 296. And the volume is 3.5. Okay, so I got 27.8 atmospheres. Okay. So another way to do this this way can be very convenient depending on the problem. To show you this way, first I'm going to convert the pressure. So I'm going to use ideal gas law, and I'm going to find the pressure of the reactants to start with. So this will be 2.5 moles of O2. I'm just going to write R, and then I have the temperature, and then I have volume. So I have 17.35 atmospheres of O2. Okay, this is going to be kind of funky, but just bear with me. I'm going to use carbon. Even though it's a solid, I'm going to pretend it's a gas for this calculation. So this is going to be 20 points. I'm going to put it in quotes, 20.61 atmospheres of carbon. Okay, of course I would never, put that if there was some kind of actual pressure needed. We don't count solids or liquids, but in terms of just doing a limiting reactant, you'll see how this can work. So now I'm going to use the ratio of 2 carbon monoxide to 1 oxygen, and this is going to make 34.7 atmospheres of CO, and then this ratio was 2 to 2 or 1 to 1. That would make 20.61 atmospheres of CO. So again, we got the lower number. We've found the limiting reactant. This way is the carbon, right? And we've now figured out how much carbon monoxide is going to be produced in atmospheres, right? And then we still need to figure out the excess oxygen. So now I'm going to do excess oxygen. So we're going to take the pressure of oxygen that we started with initially, and we're going to subtract the amount used. So if I take the pressure in quotes of carbon and do 1 O2 for 2 carbons, that's going to be about 10.3 atmospheres of O2 used up. So I'm going to subtract that. And I'm going to get 7.05, let's call it, I guess, 1 atmospheres of O2 in excess. Okay, now all we do is we have the total pressure of CO, we have the pressure of CO and the pressure of excess oxygen reagent, and the total pressure is going to be the sum of those two, which would be about 27.7, which is basically what we got. Just because of the rounding and the way we did this, it's slightly different, but close enough for us. So the point is, you can do stoichiometry with atmospheres. You can also do it with liters if you wanted to. If you had a different problem that had a constant pressure and there was, supplying oxygen at this amount of liters and something at this amount of liters, you can do stoichiometric ratios with that. So it doesn't have to be moles. So I think you'll find if you look at different problems that this can, again, like I said, come in handy and make it very convenient to do quick stoichiometric conversions. And hope that makes sense, and you can utilize this little trick, and I'll talk to you in the next video.